In this video, we discuss solving trig equations involving multiple angles. Let's get started with the examples. Solve 3x equal 1 for x between 0 and 2 pi. We notice that the given equation already has the trig expression isolated. So 3x is the angle whose sine equals 1. Thus 3x is pi over 2 plus integer multiples of 2 pi. To solve for x, we divide both sides by 3, remembering to distribute to both terms on the right-hand side. Getting common denominators on the right-hand side helps when computing those solutions in the interval from 0 to 2 pi. We will plug in integer values for k, starting with k equals 0 to compute those solutions. This amounts to adding 4 pi in the numerator. We get that x0 equals pi over 6. Adding 4 pi over 6 produces x1 equal 5 pi over 6. Adding another 4 pi over 6 gives us x2 equals 9 pi over 6, which reduces to 3 pi over 2. If we add another 4 pi over 6, we get a value outside the interval from 0 to 2 pi. Thus, we have 3 solutions in the interval from 0 to 2 pi. Notice that there are 3 solutions in one period when the original input is 3x. Now let's solve a similar equation, tangent of 3x equals 1, for x in the interval from 0 to 2 pi. Again, the trigonometric expression is isolated. This time, 3x is the angle whose tangent is 1. Thus, 3x is pi over 4 plus integer multiples of pi, since the period of tangent is pi. To solve for x, we divide both sides by 3, again remembering to distribute to both terms on the right-hand side. Getting common denominators helps when computing those solutions in the desired interval. We will plug in integer values starting at k equals 0 to compute the desired solutions. This again amounts to adding 4 pi in the numerator. When k is 0, we get that x0 is pi over 12. Adding 4 pi over 12 produces x1 equals 5 pi over 12. Adding another 4 pi over 12 gives us x2 equals 9 pi over 12, which reduces to 3 pi over 4. Adding another 4 pi over 12 gives us x3 equals 13 pi over 12, which is still less than 2 pi. Continuing, we get that x4 equals 17 pi over 12, and finally x5 equals 21 pi over 12. Adding another 4 pi over 12 would put us past 2 pi. So there are 6 solutions to this equation in the interval from 0 to 2 pi. Notice that the original input was 3x, and the interval covers 2 periods. Hence, we have 6 solutions. Now let's solve sine x minus cosine 2x plus 1 equals 0 for x in the interval from 0 to 2 pi. This equation involves multiple trig functions and multiple angle inputs. It might be convenient to rewrite cosine 2x in terms of sine x to have only one trig function. We substitute cosine 2x equals 1 minus 2 sine squared x. Then we can simplify by distributing the negative and collecting like terms. Now we have a quadratic in sine x. We can factor the quadratic expression to produce a product equaling 0. Thus, one of the factors must equal 0. So either sine x is 0 or sine x is negative 1/2. These are equations we can solve using our knowledge of the unit circle. Therefore, x equals 0, pi, 7 pi over 6, or 11 pi over 6 in the interval from 0 to 2 pi. Next, let's solve the equation sine x times cosine x equal 1 for x in the interval from 0 to 2 pi. At first glance, this equation does not appear to involve multiple angle inputs. Having a product equaling 1 is not helpful because we don't know that a factor has to be 1. In fact, there are infinitely many ways that a product can equal 1. We can multiply both sides by 2, and now we can substitute sine of 2x for 2 sine x cosine x. Thus we have sine of 2x equals 2. But this is a contradiction because the range of the sine function is from -1 to 1. Therefore, there are no solutions to the original equation. Finally, let's solve the equation sine 3x times cosine x plus cosine 3x times sine x equals root 3 over 2 for x in the interval from 0 to 2 pi. When we look at this equation, we realize that root 3 over 2 is a special value from the unit circle. The sum on the left-hand side of the equation looks familiar from the addition and subtractions formula. It's the formula for the sine of a sum. Therefore, we have sine of 4x equals root 3 over 2. So 4x is the angle whose sine is root 3 over 2. From the unit circle, we know that sine is positive in the first and second quadrants. Thus, 4x equals pi over 3, or 2 pi over 3, plus integer multiples of 2 pi. To solve for x, we divide both sides by 4, and getting common denominators helps when computing those solutions in the interval from 0 to 2 pi. We will plug in integer values for k, starting with k equals 0. This again amounts to adding 6 pi in the numerator. Leaving the denominators all 12 will aid in listing the solutions in numerical order. There are 8 solutions in the interval from 0 to 2 pi, namely pi over 12, 2 pi over 12, which we reduce to pi over 6, 7 pi over 12, 8 pi over 12, which reduces to 2 pi over 3, 13 pi over 12, 14 pi over 12, which reduces to 7 pi over 6, 19 pi over 12, and 20 pi over 12, which reduces to 5 pi over 3. Again, note that solving trig equations takes a lot of practice and experience. It's also helpful to have a ready reference for common trig identities to aid in making useful substitutions.